This is the mysterious function x to the x. Many people might wonder, how do you calculate the area under this curve from 0 to 1? Well, let's look at the graph first. Oh, that's not a very good line. Here is 1. That's not a good line either. There's the area under the curve from 0 to 1. But how do we actually compute this? So what we want to start off with is obviously the integral from 0 to 1 of x to the x dx. So some things I want to recall before we go into this integral and dive in and do all the tricks and manipulations. Let's remember what the gamma function is first. And it's n factorial equals the integral from 0 to infinity of e to the negative v to the n dv. There's many different ways to write this gamma function, but this is just one of them that will come in handy during this problem. Another thing I want to recall is the Taylor series for e to the x centered around 0, so e to the x equals the infinite series from 0 to infinity of x to the n over n factorial. Okay, now we can really dive in. The first thing I really want to do here is rewrite the integral as the integral from 0 to 1 of e to the ln x to the power of x dx. Because, I mean, if you really look at that, that's just 1, so it's the same thing. Then what I want to do is, using the property of exponents, bring this x down, so we get the integral from 0 to 1 of e to the x ln x. Now something you can do with when you have something other than just normal x in the exponent, like something like x ln x, you just plug that in for x in this formula right here. So we would get, using this expansion right here, we would get the integral from 0 to 1 of the summation from 0 to infinity of x ln x to the power of n divided by, of course, n factorial dx. So something that we can do in this problem is switch the integral sign and the summation sign. I'm not going to prove it because that would be a whole other lengthy process, but it actually ends up proving itself if we complete this integral. So here we go. We're just going to swap them, and then we're going to bring this n factorial outside of the integral because it doesn't relate to this variable x here. So we get the summation now from 0 to infinity of 1 over n factorial times the integral from 0 to, not 0 to infinity, not yet, oops, 0 to 1 of x ln x to the power of n dx. So now what we're going to do here, we're just going to rewrite this. Actually, I don't even need to, I can erase this right here. Just do x to the power of n and ln x to the power of n. Just distribute that n in the exponent. And then what we're going to do is we're going to make a u substitution, because remember, kind of what our goal here is we're trying to make this integral look like this n factorial over here. So what we're going to do is make u equal to the negative natural log of x, and then we get that du equals negative 1 over x dx, and also x, e to the negative u equals x if you exponentiate both sides of this. So now, let me scroll down. What we're going to get, plugging all these substitutions in, is the summation from 0 to infinity 1 over n factorial. And remember, we got to change those bounds because we have a u here. So plugging 1 in for our u, we get 0 on the top bound. And on the bottom bound, we get, well, what is natural log of 0? If you remember looking at the graph of natural log of 0, as it approaches 0, f of x kind of approaches negative infinity, but this is negative natural log of x, so it's actually going to approach positive infinity there on the bottom. Oops. Now what we're going to do is plug all these substitutions in, so we're going to get for x, we know that x is equal to e to the negative u, so we get e to the negative u to the power of n. We know that negative natural log of x is our u, so negative u is equal to natural log of x, negative u to the n. And then we know that dx is equal to negative x du. But we know that x, of course, is equal to e to the negative u, so we get times negative e to the negative u du. Okay, I'm going to come down here a little bit, and now we can do a few things. What I'm going to do first is reverse the orders of these bounds, just to bring a negative to the front. So that'll give us negative summation from 0 to infinity of 1 over n factorial times the integral from 0 to infinity now, because we multiplied by that negative. We can also multiply these exponents because negative u is being raised to the power of n, so we get e to the power of negative un times, we can take the negative 1 from here, raise it to the power of n, we get negative 1 to the n times u to the n, a lot of parentheses here, and then we'll just have a negative. We'll have a negative 1 times e to the negative u du. That's a lot of stuff there. So now there's a few things we can do now. We can cancel these negatives here. We can bring this out to the front because it doesn't relate to u. So let's do that. So this is equal to the summation from 0 to infinity of now negative 1 to the n over n factorial times the integral from 0 to infinity of, and it'll be e to the negative u n. I'm actually going to put this next to it. You'll see why in a second. Hold on, that's supposed to be un e to the negative u, and then of course we have u to the n du. Next, what we're going to do here, I'm just going to erase it, I don't want to rewrite this. We're going to combine those exponents. So we're going to get negative u to the n minus u times u to the n du. So this now, this is equal to the summation from from 0 to infinity of negative 1 to the n divided by n factorial times the integral from 0 to infinity, and we can factor out a negative u here, so we get e to the negative u times n plus 1 times u to the power of n du. Now this is starting to look more and more like this gamma function up here if we look at it. So the next step, what we're going to do is, I mean, it's basically the gamma function. All that's missing is that v right there. So what I'm going to do is I'm going to set v equal to u times n plus 1, and then dv will be n plus 1 du, and if we divide by n plus 1, u is equal to v divided by n plus 1. So let's just, this is almost the last step, honestly. So what we're going to do is we're going to plug these substitutions in. So we're going to get the summation from 0 to infinity of negative 1 to the n divided by n factorial times the integral from 0 to infinity. That was a terrible infinity. Come on. That was a big one. And now we get, so it'll be e to the negative v, right? Because our v was u times n plus 1. So we get e to the negative v what was our u? Our u was v over n plus 1. So we're going to get v over n plus 1 all to the power of n. And then our du was dv divided by n plus 1 times dv divided by n plus 1. So, almost done here. What I'm going to do is, I'm going to take that parentheses off. I'm going to raise this to the power of n and this to the power of n. You'll see why. Now we rewrite this, of course, as I've done many times now. Integral from 0 to infinity of e to the negative v, v to the power of n, divided by n plus 1 to the power of n plus 1, because this is raised to the first power and this is raised to the nth power. Now, this is now pretty much the gamma function, because we can bring this whole n plus 1 to the n plus 1 term out, because it doesn't relate to v. So that's pretty awesome. And we get summation from 0 to infinity. This is going to be a super lengthy term out here now. We're going to get n factorial times n plus 1 to the power of n plus 1 times, this is the last time we'll have to write this integral, e to the negative v, v to the power of n, dv. So now this is where the real magic happens. As I stated earlier in this integral, the integral from 0 to infinity of e to the negative v times v to the n dv is actually equal to n factorial. So this whole term right here, n factorial. So what we're going to get is this summation as a horrible infinity, once again, n factorial times n plus 1 to the power of n plus 1 times n factorial. These n factorials are going to cancel. And what is this? This is an alternating series, so we can actually, using technology, approximate the solution. And using it, we find that the solution is around 0.783. And there's our solution. So therefore, the integral from 0 to 1 of x to the x dx approximately 0.783. And there we go. I hope everyone enjoyed this video. This was the Bernoulli integral. And if you want to find out about similar classes of integrals, just look up Bernoulli integrals, and you'll find a whole class of functions that are really interesting to integrate. Thanks for watching.